In the summer of 1858, a Swedish merchant stood in a small ironworks north of Stockholm and watched a converter full of molten iron destroy everything he owned. His trading house had already collapsed. His creditors were circling. The process he had staked his fortune on had failed in England, in front of the men who invented it, and every ironmaster in Europe had written it off as a fraud. Göran Fredrik Göransson was about to make it work anyway. What nobody knew at the time was that the fix he found that July, a change to a row of nozzles most engineers would have called trivial, would launch the modern steel age, save Henry Bessemer's reputation, and seed a company that eventually built the cutting tools inside almost every jet engine, engine block, and hip implant on the planet. This is Trade Archive. If industrial history is your thing, hit like and subscribe. It genuinely helps. Edske, Sweden, 1857. Göransson was not an engineer. He was a merchant from Gävle, a port town on the Baltic coast, born in 1819 into a world where Swedish iron moved by sled and barge, and the technology of ironmaking had barely changed in 2 centuries. He was a partner in a trading house called Daniel Elfstrand Co, and in 1856 that firm bought a bruk, a Swedish ironworks estate, at Högbo, along with a blast furnace at Edske. The next year he sailed to England to buy a steam engine. He came back with something else entirely. While he was in London, he attended a demonstration at Baxter House, where an inventor named Henry Bessemer was showing off a process that sounded like alchemy. Bessemer's idea was to blow cold air straight through molten pig iron. The carbon in the iron would catch fire and burn off, and the burning carbon itself would generate enough heat to keep the whole mass liquid without any external fuel at all. 20 minutes of roaring white flame, and you had steel. Not the tiny crucible batches that blacksmiths had made for centuries, but tons of it, in a single pour. The problem was that it did not work. Bessemer had licensed 5 British ironmasters, and every one of them had produced garbage. The steel came out brittle, riddled with slag, useless for rails or plate or anything else. British pig iron was loaded with phosphorus, which survives the blow and wrecks the metal. The blast also left the steel saturated with oxygen. Bessemer went from celebrated to humiliated in a matter of months. The Encyclopedia Britannica later recorded the verdict of the era plainly, noting that Göransson, using the purer charcoal pig iron of Sweden, was the first man to make good steel by the process, and that even he only managed it after many attempts. Göransson had watched the demonstration, read the damning reports, and bought in anyway. He purchased a 1/5 share of the Swedish rights to Bessemer's patent for roughly £2,000. The license allowed him 500 tons a year at a royalty of 2 shillings per ton. He was buying into a technology that the entire British iron trade had just declared worthless. The Swedish Ironmasters Association advanced him 50,000 kronor to run experiments. He needed all of it. The first blows at Edske produced porous, bubbling metal, full of gas holes, exactly as useless as the English attempts. Every failed heat burned charcoal, burned pig iron, burned wages, burned time. And by December of 1857, Daniel Elfstrand Co was in severe financial trouble, the kind a merchant house does not usually walk away from. His backers kept funding him anyway, not out of sentiment. They kept funding him because the failures were getting less bad. Göransson had worked out 2 things his English counterparts had missed. The first was chemistry. Swedish pig iron was smelted with charcoal rather than coke, and Swedish ores were low in phosphorus, which meant the raw material was clean in a way British iron simply was not. The second was airflow. The Bessemer converter fed its air blast through tuyeres, the nozzles set into the bottom of the vessel. Göransson had the upper row of tuyeres removed entirely and enlarged the ones in the lower row, then pushed the blast harder and hotter. The theory was that a stronger, more concentrated blast would keep the bath hot enough for the slag to separate cleanly instead of getting trapped in the metal as it cooled. On the 18th of July, 1858, they ran a heat through the modified converter. The steel flowed easily. The grain was close and dense. The gas holes were gone. That is the whole moment. No lightning strike, no crowd, just a merchant standing in a shed at Edske, watching good steel pour for the first time in industrial history, having spent a bankruptcy and a year of his life to get there. Later that year, Göransson went back to London and told Bessemer he had done it. Bessemer, by his own account, did not believe him at first. Göransson brought samples. He won the right to sell his steel in England, and when Bessemer opened his own works in Sheffield, he ran it on imported Swedish charcoal pig iron because it was the only feedstock that reliably behaved. When Göransson died in 1900, his obituary put it bluntly. Without his help, the Bessemer process might never have been perfected. Göransson had solved the technical problem. He had not solved the money problem. On the 31st of January, 1862, he founded Högbo Stål Jernwerks AB and chose a site on the shore of Lake Storsjön, a place called Sandviken, Sand Bay. There was almost nothing there. Within a year, he had cut a canal to move material, fired up a blast furnace and Bessemer converters, installed one of the largest steam hammers in Europe, and built a mill for rolling railway wheel tires, which were the high-margin product of the age. He built fast, he built big, and he built on credit. The 1860s were a brutal decade for Swedish capital. By 1866, with the credit market frozen and the works consuming cash faster than it earned, Göransson and his company went into receivership. Again. The man who had personally rescued the most important steelmaking process of the 19th century had now been financially destroyed by it twice. The works was sold off in a distress sale and reconstituted in 1868 as Sandvikens Jernverks AB. Göransson's son, Anders Henrik, took over as managing director. A financier named Per Murén became chairman. The founder himself was pushed out of executive control of the company he had built and did not become chairman until 1883, when he was 64 years old. The company survived on the thing Göransson had actually mastered, which was quality. Sandvik steel developed a reputation as the cleanest, most consistent material available anywhere, and the firm leaned into products where that mattered. Steel bar, wire from 1876. Cold-rolled strips so thin and so uniform it could be wound into watch springs and gramophone springs. Umbrella ribs. In 1886, they shipped their first hand saw, and Sandvik saws would end up in workshops across Europe for the next century. The name itself was almost an accident. Sandvik was first used officially as a brand at the Philadelphia World Fair in 1876, stamped onto steel bar so buyers could identify where it came from. That stamp became one of the most recognized marks in the global metals trade. Then, in 1877, prices halved. Murén put his own capital in to keep the doors open. That is, twice in a decade the company came within an accounting decision of not existing. And this is the pattern worth holding on to, because it repeats. Sandvik has always been a company one bad year away from extinction that survives on the strength of a single technical advantage nobody else has. By 1898, the Bessemer age had peaked, and Sandviken installed Siemens Martin open hearth furnaces, which were slower but far more controllable. Göransson died in 1900. The company listed on the Stockholm Stock Exchange the following year. What happened next set up everything that came after. In 1907, Sandvik began making hollow drill steel for rock drilling. Hollow steel let compressed air and water run down the middle of the drill rod to flush rock cuttings out of the hole, and it required exactly the kind of clean, tough, precisely rolled material Sandviken was built to produce. That single product line put Sandvik into the mining business, and it put Sandvik into the business of making things that other people used to cut hard material. In 1921, Sandvik started producing stainless steel and posted its first loss since 1868. The post-war slump was savage. Unemployed workers at Sandviken petitioned to draw down their own pension savings just to eat. 3 years later, the company rolled its first seamless stainless tubes, and by 1934, it was the first firm in Europe pilgering tubes at industrial scale. Sandviken, by this point, was not really a town with a factory in it. It was a factory that had grown a town around itself. Housing, schools, a foundation the founder had set up in the 1860s to support workers and their families. Generations of the same families went through the same gates. That mattered later. Then came a war, and a shortage, and a material that cost more per gram than gold. Cemented carbide was not a Swedish invention. It came out of Germany in the 1920s, from a researcher named Carl Schroeder working at Osram, the lamp company. Osram had a very specific problem. Drawing tungsten filament wire for light bulbs destroyed conventional dyes almost immediately, and diamond dyes were ruinously expensive. Schroeder's answer was to take tungsten carbide, which is fantastically hard and completely unworkable on its own. Grind it to powder, mix it with a small amount of cobalt, and heat the mixture until the cobalt melted and glued the carbide grains into a solid mass. The patent was filed on the 30th of March, 1923. Krupp licensed it and put it on the market as Widia, short for Y-Diamant, German for like diamond. In its first years, 1 gram of the stuff cost more than 1 gram of gold. By the late 1930s, carbide had become a strategic material, and in Sweden it was scarce. The Swedish Cooperative Association's Luma lamp factory in Stockholm was producing it, largely for military use. In 1942, in the middle of a war Sweden had declared itself neutral in, while the industrial economy around it ran red-hot, Sandvik signed a 10-year agreement with Luma that transferred exclusive rights to process carbide for civilian production. Sandvik now had a material almost nobody could get. What it did not have was any idea what to do with it. The job went to a 39-year-old engineer named Didrik Wilhelm Haglund, who had joined the company in 1925 and had been in the works ever since. He was handed a small division, a scarce powder, and no established market. The name came from Carl Siebart, a production manager. Sandvik's high-speed steel was already sold under the brand Corona. Siebart fused Corona with diamant, the Swedish word for diamond, and got Coromant, sun and stone. It was a marketing decision made in a wartime factory that ended up on toolboxes in every industrial country on Earth. The first Sandvik Coromant carbide cutting tools were manufactured in 1943. What Haglund's division was actually doing on that shop floor is worth slowing down for, because the process has barely changed in 80 years, and it is nothing like conventional metalworking. You start with tungsten ore, usually scheelite or wolframite, and chemically process it into ammonium paratungstate, a white crystalline salt. That gets converted to tungsten oxide, then reduced with hydrogen into gray tungsten metal powder. The powder is mixed with carbon and fired, which carburizes it into tungsten carbide. Now you have a black powder harder than almost anything in the natural world, and completely useless, because you cannot cast it, forge it, or machine it. So you blend it with cobalt powder, wet mill the mixture for hours in a ball mill, and spray dry the resulting slurry into a free-flowing granulate that looks a bit like instant coffee. That granulate gets pressed into a die under enormous pressure, producing a green body, a compact so fragile you can crumble it between your fingers. Then it goes into the sintering furnace. Somewhere between 1300 and 1500 degrees Celsius, the cobalt melts and flows into every gap between the carbide grains by capillary action, pulling the whole structure inward. The part shrinks by roughly half its volume. It comes out of that furnace as a single dense body of tungsten carbide skeleton locked in a metallic cobalt binder, and it will now cut hardened steel. Every decision in that chain is a trade. Finer grains and less cobalt give you a harder, more wear-resistant tool that chips if you look at it wrong. Coarser grains and more cobalt give you toughness at the cost of edge life. That balance, grade by grade, application by application, is the entire science of the industry. In 1944, before it had a real product line, Coromant did something that told you what kind of company it was going to be. It set up grinding stations so customers could get their carbide tools reground and repaired, and so Sandvik engineers could stand next to those customers and watch how the tools actually failed. The company was collecting field data on wear patterns 2 decades before anyone called that a strategy. The war ended. In 1947, the last Bessemer heat was blown at Sandviken, closing out the process the founder had rescued 89 years earlier. The same year, Sandvik became the exclusive supplier of carbide-tipped rock drill steel to Atlas Diesel, later Atlas Copco, creating what the mining world came to call the Swedish method. Carbide demand was climbing faster than Sandviken could handle. In 1951, Sandvik bought a disused joinery workshop belonging to the Korsnäs Forestry Company in a small town called Gimo, along with a parcel of land, for 1.5 million kronor. A furniture factory in rural Uppland became a carbide plant. Today, Gimo is the largest facility of its kind in the world. In 1953, the company opened a dedicated carbide plant at Västerberga in Stockholm and started production in Fair Lawn, New Jersey. The American market was the prize, and the Americans were not interested. Here is what the shop floor looked like in 1950. A lathe operator running a turning job used a solid tool, either high-speed steel or a piece of carbide brazed onto a steel shank. When the edge went dull, and it always went dull, the machine stopped. The tool came out. Somebody carried it to the grinding room, reground the geometry by hand and by eye, and carried it back. On a bad day, a skilled machinist spent more time at the grinder than at the machine. Sandvik's answer, developed in 1954 and 55, was called Gamax. A small piece of precisely shaped carbide, clamped mechanically into a steel holder. When the edge wore, you released the clamp, rotated the insert to a fresh corner, and reclamped. Seconds instead of an hour. Nobody reground anything. When all the corners were used, you threw the insert away. Throwaway tooling. In an industry built on the idea that you regrind and reuse everything, that was close to heresy. Gamax opened the door. What kicked it in was T-Max. In 1957, a manager named Sven Vierfeldt took the T-Max holder system to the United States. T-Max was a clamping mechanism, and clamping was the whole problem. An insert that shifts even fractionally under cutting load is worse than useless, because now your dimensions are wrong and your edge is chipping. T-Max held the insert rigidly and repeatably and critically. Sandvik had worked out how to produce the inserts themselves more cheaply than anyone else could. That combination is what won it. Not just a better tool the customer could afford to throw in the bin. Sandvik's own histories describe what followed as a triumphal progress, which is not a phrase Swedish engineering firms use lightly. The Americans were skeptical for a reason worth understanding. American machine shops were built around skilled tool grinders, men who had spent 20 years learning to put a geometry on a piece of high-speed steel by hand and by feel. Telling a shop to throw the tool away was telling those men their skill was obsolete. Vierfeldt was not selling a product into a purchasing decision. He was selling against a trade's sense of itself. He won because the math was brutal. A machine standing idle costs money every minute. Once a shop ran the numbers on downtime, the argument was over. T-Max reached Europe in 1958. That same year, Hägglund became managing director of the entire Sandvik group, and control of the company passed from the Göransson family to the Stenbeck family through a new share issue. The founders' descendants were out. The engineer who had been handed a scarce powder and a small division 16 years earlier was now running the whole thing. Hägglund's stated position, from 1959, was 3 words: no more redundancies. Coming out of the layoffs and losses of the previous decades, in a company town where the works and the community were the same thing, that was a promise with teeth in it. By the early 1960s, Sandvik held a commanding lead in indexable inserts across Europe, and in 1961, they released the product that paid for everything else. It was catalogued as Insert 170.6. Everyone called it KNUX. It was a turning insert, and by the company's own account, it stayed a top seller for more than 30 years. 3 decades is an extraordinarily long life for a consumable in a market where geometry moves constantly, and it points at something structural about this business. Inserts are consumables. They wear out by design. Every insert sold is a customer who will need another one, and a factory that standardizes on your holder system is a factory that buys your inserts for the working life of the machine. Sandvik was not really selling tools. It was selling a standard and then selling the refills. Which is why the next move was education, not engineering. In 1965, Sandvik opened the first Coromant school at Sandviken, running 5-day residential courses. Machinists and production engineers from customer plants came to Sweden and learned metal cutting theory, feeds and speeds, chip formation, tool wear mechanisms. Sandvik was teaching an entire generation of engineers how to think about machining, using Sandvik's vocabulary and Sandvik's numbers. Graduates went home and specified Sandvik tooling for the next 40 years, and never really considered it a marketing exercise, because it was not one. The training was genuinely good. That was the point. The same year, Coromant introduced the ejector drill, a long hole drilling system with brazed carbide inserts. By 1967, the group had 40 subsidiaries and sales in 100 countries. Then, in 1969, Sandvik Coromant did the thing that reordered the industry. CNC machines were arriving, and they ran faster than anything before them. At high cutting speeds, the interface between insert and workpiece reaches temperatures that soften carbide and let the workpiece material weld itself onto the cutting edge. Speed was capped not by the machine, but by the tool's ability to survive its own heat. Sandvik's solution was to stop treating the insert as a single material. In 1969, the company introduced gamma coating, the first surface-coated cemented carbide insert in the world. A microscopically thin ceramic layer was deposited onto the carbide substrate by chemical vapor deposition, gas reacting on the hot surface and building up a film measured in microns. The substrate underneath stayed tough. The skin on top was ceramic hard and thermally resistant, so heat that used to soak into the carbide got kept out of it. Metal cutting performance jumped by as much as 50%. Every coated insert made anywhere in the world today, by any manufacturer, descends from that. By 1972, the company had renamed itself Sandvik AB, and its field engineers had started wearing the yellow coat that became the brand's signature on shop floors from Detroit to Nagoya. 1976 brought T-Max U, the first short hole drill using indexable carbide inserts, which took drilling out of the twist drill era it had been stuck in since the 1860s. By 1977, more than 90% of Sandvik's sales came from outside Sweden. In 1980, Sandvik went after the last bottleneck. Cutting was now fast, but changing tools was slow, and every machine minute spent swapping tooling was a minute not making parts. The block tool system split the tool into a cutting head and a permanent base so the head could be changed in seconds without touching the machine setup. 3 years later, everything went wrong. 1983 delivered Sandvik's first loss in 62 years. Ownership shifted again to the construction group Skanska, and Percy Barnevik, then running ASEA and about to become one of the most consequential industrialists in Europe, took over as chairman. Under pressure, the company decentralized into separate business areas and pushed into new materials, launching ceramic and cubic boron nitride inserts. The pattern from 1866 and 1877 held. Near collapse, restructure, ship better technology than anyone else. The technology that came out the other side arrived in 1990, and it is still an industry standard. Coromant Capto is a coupling, the joint between the tool and the machine spindle. The name is Latin, meaning to seize or grip. Instead of a cylindrical shank or a steep taper, Capto uses a tapered polygon, which resists the torque of heavy cuts and locates the tool the same way every single time. It was so structurally sound that competitors adopted it, and it was eventually written into international standard ISO 26623. Sandvik designed the connector and then let the world use it, which is how you turn a product into infrastructure. In 1994 came the first industrial-scale diamond-coated carbide inserts. In 1997, Sandvik started collecting used carbide from customers to reclaim the tungsten and cobalt inside it. Then came a problem that no coating could fix. If you bore a deep hole or reach a long way into a component, the tool acts like a tuning fork. Vibration builds, the surface finish tears up, the edge chips, the spindle takes damage, and the noise is genuinely unbearable. Machinists call it chatter, and for a century, the only answer was to slow down. In 2008, Sandvik bought a Norwegian company called Tuyeres, based in Trondheim, and with it the technology that became silent tools. The solution is mechanical rather than electronic. A heavy tuned mass is suspended inside the boring bar itself, supported on rubber elements and immersed in oil. When the bar deflects one way, the mass moves the other, and the vibration energy gets absorbed instead of amplified. It lets a shop run overhangs of up to 14 times the bar diameter, which is territory a solid steel bar cannot enter at all. In 2013, Sandvik went after the coating itself at the atomic level. In a normal ceramic coating, the aluminium oxide crystals grow in random orientations, like bricks tipped into a pile. Sandvik found a way to control that growth so every crystal aligned in the same direction, with its hardest, most thermally resistant plane facing the cutting zone. They called it Inveo and launched it on grade GC4325. It is one of the few genuine material science breakthroughs the industry has produced this century. 4 years later, in 2017, they went after the geometry of turning itself. Conventional turning cuts from the end of the workpiece toward the chuck, which loads the fragile nose of the insert with all of the heat and pressure. Prime turning inverts it. The tool enters near the chuck and cuts outward, allowing a small entering angle that spreads the load across a longer, stronger stretch of cutting edge. Sandvik reported productivity gains above 50%. Turning had been done essentially one direction for as long as there had been lathes. In 2019, the World Economic Forum named the Gimo plant, that converted furniture workshop from 1951, an advanced manufacturing lighthouse. The citation singled out its digital thread, a chain running from design data straight to the machines, and touchless changeover, where the plant reconfigures itself for a different product without a human on the floor. Gimo runs shifts with nobody in the building. But the tools that build the world ended up in places the manufacturer never intended. Sandvik has operated in southern Africa since 1948, supplying rock drilling equipment to the mining industry, which meant it was present and profitable in South Africa throughout the apartheid era, and it faced sustained criticism at home in Sweden for it. And after Russia's full-scale invasion of Ukraine in 2022, Sandvik suspended and wound down its Russian business, taking around 1.5 billion kronor in charges, having employed roughly 900 people there. Swedish media later reported that Sandvik goods still reached Russia through third countries, which is the standing problem with sanctions on industrial equipment. Machine tools are not weapons. They are what weapons are made with, which brings up the constraint that now shapes the company's strategy more than any competitor does. Tungsten is roughly 3/4 of the weight of a cemented carbide tool, and the world does not have much of it. Global reserves run to a few million tons, concentrated in a handful of countries, several of which are geopolitically difficult. Sandvik has responded by closing the loop. It bought an Austrian tungsten producer, Wolfram Bergbau und Hütten. It buys back worn inserts from customers at market rates, and it chemically breaks that scrap down to recover tungsten and cobalt powder that performs identically to virgin material. Making carbide from recycled feedstock uses around 70% less energy than making it from ore. Sandvik's rock tool grades now run up to 3/4 recycled content. The company that started by refining someone else's failed process now stays alive by refusing to throw anything away. In April 2026, Sandvik bought 80% of K&Y Diamond, a 45-person firm in Montreal founded in 1976 that makes monocrystalline diamond tools for ultra-precision optics. Contact lenses, spectacle lenses, optronics. Roughly 120 million kronor of revenue. In group terms, it is a rounding error. In strategic terms, it is the same move Sandvik has made for 160 years, which is to buy the sharpest available edge and industrialize it. The Sandvik Group today turns over around 120 billion kronor, with roughly 42,000 employees. Sandvik Coromant accounts for about 8,000 of them and sells into more than 150 countries. Wilhelm Haglund died in 1987. Sandvik still awards a medal in his name for the most significant contribution to a company product, and the technical secondary school in Gimo carries his name, sitting a few minutes from the sintering furnaces that shrink pressed powder into steel cutting tools by half their volume every day. Göran Fredrik Göransson went bankrupt twice, lost executive control of his own company, and spent most of his working life financially exposed to a process that everyone competent had already declared a failure. What survived him was not a fortune. It was a standard for what clean, consistent, engineered material should be, carried forward through hollow drill steel and stainless tube, and a scarce gray powder that a wartime engineer turned into an industry. Very little of what you own was made without something Sandvik built first. If this is the kind of history you want more of, the machines and the metallurgy and the people who bet everything on both, subscribe to Trade Archive. There is another one coming.